Thank you very much, and hello, everyone. I would like to start by acknowledging the traditional owners of the lands that we're meeting on today, and that is the Gadigal people of the Eora Nation, and would like to pay my respects to elders past and present. So if you're new to Australia, you might not be aware that Australian Indigenous people have a very long history here. They've been living in Australia for about 65,000 years, which makes them the oldest continual culture in existence across the whole world. And they have a very, very rich old knowledge that I always think there are opportunities to combine with the kind of modern technological knowledge that we have nowadays. They are passed on through generations. They have ways of good land management practices. They were Australians' first astronomers. In fact, their version of astronomy looks not just at the stars, but the black space between the stars has just as much significance. So I think there's a real opportunity with Indigenous cultures all over the world to actually combine the age-old knowledge and practices that they have with modern technologies like artificial intelligence. And to illustrate that, I wanted to just start with a little video.
I know how who kunugena ngatu opir kongari ira mbiri malmangi KJB mani muna change kongari what give me
I'm a proud Larrakia man, and I work here in Kakadu as a Cultural Heritage Officer. Our country and traditional owners have always been connected. We have gathered knowledge across the seasons to listen to the country. We need to find the best ways to care for the land, using our knowledge and new learnings. Magpie geese are an indicator of the health of our country. Watching the patterns of the geese, they tell us where extra care is needed. A dense weed called paragrass is overrunning wetlands and destroying where magpie geese live. We're using drones to monitor parts of the wetlands. They help us see the areas of the park which need our care. We're combining this information with our knowledge, Microsoft AI and science to change the way we work on the ground. It's showing us new ways to manage wetlands and help the magpie geese thrive. With this information in our hands, traditional owners can be front and centre in decisions made about country. Every day, we work to look after Kakadu. We're making sure it's here for future generations.
So this was a project that some colleagues of mine at CSIRO did with some Indigenous rangers in Kakadu National Park, which is way, way, way up in the northern part of Australia. And it's a good example of where we were combining the centuries-old knowledge that the Indigenous rangers have with modern technologies like AI, drones, computer vision. The problem they were trying to solve, as you saw there, was that there was a declining number in magpie geese because of an invasive species. And it's over a very, very vast expanse. It was very, very difficult to track that invasive species and manage it. But using AI tools and drones, we worked with Microsoft on that. We were able to actually do that and bring back some of the natural population of magpie geese. Let me tell you a little bit about CSIRO in case you don't know anything about it. So CSIRO is Australia's national science agency. We have offices all across Australia. So I think about 49 different sites right now. Currently about 6,000 staff, consisting of research scientists, engineers, and support staff across every possible scientific domain you could imagine, whether that's environmental science, manufacturing, healthcare, computer science, of course, energy, and pretty much every aspect of science. And we really exist to help solve some of the world's greatest challenges using science. We're a very, very multidisciplinary organization because we're all under one roof. I think we're one of only 2 national science agencies in the world where you have all the scientific disciplines all under one roof, which means we can collaborate together very, very seamlessly. It's a very long history that we've got in CSIRO. We're an organization that's over 100 years old, but I just want to share 2 claims to fame that we often talk about. So the first is that an Australian antenna in 1969 was the first to receive live video footage from the moon. You know it, you've seen it, one small step for man, one giant leap for mankind. That was received by the antenna on the left live in Australia in 1969. And that antenna is currently at a CSIRO facility just outside Canberra, which is still used today, and it's a tracking station that we work very closely with NASA to track things like the James Webb Telescope, for example. There's an interesting story behind this because the telescope on my left is the Parkes telescope that is in New South Wales. That was the telescope that was supposed to receive the footage. But what happened is that when the lunar lander landed on the moon, Neil Armstrong and his colleagues were supposed to wait for a few hours so that they could rest before taking their famous first step on the moon. However, as you can imagine, if you've just landed on the moon, you're probably quite excited. And do you really want to sit around waiting for a few hours before you see what it's like? Neil Armstrong didn't. And so he radioed back to Earth and said, "I'm not waiting, I'm going." And they said, "Okay," but that presented a problem. And the problem was that the moon was not high enough in the sky for the Parkes telescope on my left to receive the signal. They did have an antenna in the US, in Gladstone, that could receive the signal, but it had a problem as well. There was a technical fault that meant that the image that they were receiving was upside down. And probably nobody wants to live stream the first footage from the moon to millions of people across the world upside down, right? So what did they do? Fortunately, this antenna on the right, which is called the Honeysuckle Creek Tracking Station, was a smaller antenna than Parkes, and it wasn't meant to pick up the footage, but it could pick up the footage from the moon, even at its low kind of angle in the sky. And hence, history was made, and Neil Armstrong's footage was first broadcast from that antenna, received from that antenna in Canberra in Australia. So that's one claim to fame. Another claim to fame, if you did not know this, CSIRO invented fast Wi-Fi. Wi-Fi was already around. This was in the 1990s, but there was a big problem using Wi-Fi, particularly in indoor environments, and that was that there was a lot of noise with the signal kind of bouncing off objects, and nobody knew how to solve this problem. Now, it turned out that a bunch of radio astronomers in Australia were trying to detect black holes. And black holes give out signals that are also very noisy. And so they invented a technique to reduce the amount of noise in that signal, which was intended to allow them to detect black holes out in the outer galaxies. But for some reason, I don't exactly know why, they ended up applying that problem to Wi-Fi, and they reduced the issue of what they call reverberation, which is the indoor signal noise, which then led to Wi-Fi being able to be scaled up in indoor environments in a way that we would never have seen before. So fast Wi-Fi was invented in Australia. I have to say, however, that they never detected the black holes that they were trying to find. But I think as a society, we're probably willing to take that trade-off because we got fast Wi-Fi out of it. Data 61 is the part of CSIRO that I run. It's the business unit within CSIRO that does all things digital and data. So we do a lot of work in AI, cybersecurity, software engineering, human-computer interaction. About 500 staff and 300 affiliate staff across the whole of the country. I just want to give you a few kind of highlights of the type of work that we do. So first of all, we have a very big robotics team up in Queensland, field robots. They competed a couple of years ago in a DARPA Grand Challenge, which ran for 3 years and asked teams from all over the world to create teams of robots that could autonomously go underground and search for objects. They might be underground mines or underground metro stations and things like that. And the kind of use case for this is that you might have a mine collapse. You don't want to send first responders down there because it's too dangerous, but you could send robots down there because they can search for stranded people in a way that humans wouldn't be able to. So we competed with Georgia Tech and a local startup called Emerson in that competition. We had teams of 6 robots, 2 drones, 2 Boston Spot dog-like robots, and 2 robots on tracks that autonomously went down into underground environments they'd never seen before. They mapped them out. They communicated with each other. They found objects. And at the end of that 3-year journey, of all the teams that were competing, there were 2 teams that were equal on points, one of which was our team. So what did the organizers do? Because they had to pick a winner, right? They did a count back, a tie break. Unfortunately, we lost on the tie break. So officially, we are the 2nd best in the world in putting robots underground. However, I always like to say that we are equal first in the best in the world in putting robots underground. We also put robots in space. This is footage from the International Space Station. So we have Australian technology on the International Space Station as we speak. This is a project that we did with NASA. And that little floating object that you see there is called AstroBee. That is an astronaut's AI assistant robot. It floats around the International Space Station, and the astronauts can give it tasks like, go and find an object and things like that. We repurposed the 3D mapping technology that we'd used for those underground environments, and we put it on that robot, and we launched it into space. And if you go out this evening and look up into the night sky, and you can find the International Space Station, then when you do that, just think that there is Australian world-leading AI technology on that International Space Station as we speak. But it's not just in space or underneath the Earth where we do a lot of our work. We also do a lot of our work in helping to preserve the environment in which we live. As many of you will know, because it's the same in your countries, bushfires or wildfires are a big problem nowadays and are becoming increasingly a problem with climate change and raising global temperatures. So we developed an AI system called Spark, which will give you real-time predictions of where bushfires will go next. So it analyzes lots of data about the weather, about the terrain, about historical movements of bushfires and so forth. That system has been very, very successful. It is now being rolled out nationally and actually used in practice to help firefighters fighting these fires so that they can get resources to exactly the place that they need them that can therefore present, whole communities being kind of burned down by fires. So that's a kind of snapshot of some of the kind of work that we do. Today, though, what I really want to focus on is some work that we've been doing probably over the last 2 years now in this, what I called an emerging field of AI for science. So trying to use AI to accelerate scientific discovery or even to enable discoveries that otherwise wouldn't be possible. And the first thing I will say to this, although there's a lot of excitement about AI for science because of things like AlphaFold nowadays, it's always important to know your history. And actually, if you go back to the very, very early days of AI for science was very much a hot topic. You might remember some of these systems on this slide from when you studied AI. Systems like Dendril, for example, that was a very, very early expert system for scientific discovery. And it was designed to infer chemical structures from mass spectrometry data, all the way back in 1965. Then there was, of course, the Mycin system, another expert system for diagnosing bacterial infections, and that would recommend antibiotics based on patient data. So very early AI for science example. Prospector in the late 1970s was more in mineral exploration and geology, looking at predicting where ore deposits were. And then there's this system called Bacon by Pat Langley that was a system, an AI system that could automatically discover various kind of physical laws. So there's a very, very rich history of AI for science, right back to the very, very early days. But it's certainly true that in most recent years, we've seen a surge in interest in looking at applying AI to accelerate scientific discovery. AlphaFold, of course, is probably the most famous example of this, and that's already led to computer scientists winning a Nobel Prize for chemistry. But it's not the only example. We've seen a lot of large language models that are specifically designed to capture knowledge about scientific domains. For example, MedPalm that came out of Google, which is a large language model for medical knowledge. So that's been quite a large trend. GNOME, you might have read about GNOME. This was a Google system. There was an AI system for developing for discovering new crystal structures. And I think something like 2 million new crystal structures that it actually discovered. And we've even seen systems that are trying to use robots to carry out scientific inquiry as well. So there's an IBM system from a couple of years ago called RoboRxN, which is a kind of full automated end-to-end scientific lab where not only are there things like large language models coming up with scientific hypotheses, but you can actually get robots to carry out real experiments autonomously in a real wet lab, in a real setting. So lots and lots of interest in recent years in this area of AI for science. I do want to point out a few what I would see as very kind of influential reports in this area. And if you are interested in this area, I would recommend going to read these reports as a kind of starting point. So the first one I want to mention is a report called AI for Science that came out from Argonne National Labs in 2019. So fairly early in the current cycle. But what this did, it brought a whole bunch of researchers together who were in the early days of trying to apply AI in different scientific domains and kind of synthesized together what were the major challenges for research institutions that were trying to do this. And it's still today, I think, a really, really good report about, what are the kind of implications for high-performance computing, for kind of replicability of science and various other things. It's an excellent report if you want to kind of get on top of what is happening in AI for science. We brought out our own report in 2022, and what we did, we wanted to track trends of where AI was being used in different scientific disciplines, because anecdotally, I think we know that AI is being used more and more in scientific disciplines, but we wanted to chart how that has actually changed over time in fields, as diverse as you can imagine. So some people in my team did a bibliometric analysis of 60 years of academic papers across all scientific disciplines, and essentially produced a bunch of very nice graphs that showed where AI was being used in those scientific disciplines. All the graphs look the same. They're all exponential. So we've seen an absolute surge in the last few years in the use of AI in science. In fact, one stat from that report is that almost 6% of all research across all scientific fields is now done using AI in some way, shape, or form. And bear in mind, this report was published in 2022. So that was before the current Gen AI craze. So if we were to repeat that now, I'm sure we'd see even a steeper exponential graph. There's a couple of other reports worth mentioning. Royal Society in the UK brought out a AI for Science report, I think in 2024. And for those of you who read Stanford's AI Index that comes out annually, you may have noticed that in the most recent version, there's a whole chapter devoted to AI in science. And one of the stats that I like there, for example, is that even in the year 2024, there's been 9 new major scientific foundation models that have come out. So this is a huge area of interest and a very emerging area, and I think one where we're going to see a lot more excitement and interest in the years to come. Let's just step back a minute, though, and ask, what is AI for science? I've used that term probably about 20 or 30 times so far, and I haven't even defined what it means. And one thing that you will find is that people use this term AI for science in slightly different ways, depending on their background, what they're doing in the context, and so forth. So I like to think that there are at least 5 different meanings for AI for science. So the first is just, straightforward application of AI. You take some off-the-shelf AI tools, you're a scientist working in a particular domain, and you apply those tools, some kind of standard out-of-the-box kind of machine learning techniques, for example, and you apply that to your very, very specific problem. That's one. 2 is people that are trying to use, deep learning and neural networks and so forth to replace traditional scientific methods, scaling up computational simulations or replacing numerical solvers with deep learning and things like that. So kind of changing the computational method. That's another definition of AI for science. Scientific foundation models is a third definition, a more recent definition. Again, we've seen lots of those. And Department of Energy, Argonne National Labs in the US, I think, has really been leading the way. If anybody knows about the Trillium Parameter Consortium, they've been trying to do this kind of thing for a few years now with people like Rick Stevens. The fourth definition, which I think is a bit newer, is what I'd call general AI assistance. So moving away from trying to apply AI to one specific problem, but instead coming up with AI assistants, often agentic AI assistants, that try to be very, very general and apply to all areas of science and to all possible scientific workflows that scientists can imagine. So the analogy there is it's a bit like the transition from traditional AI to generative AI, where traditional AI was machine learning applied to very, very specific problems. We've now moved to generative AI, which you can use ChatGPT to write a business strategy, but you can also use it to write a poem for your friend's birthday, right? It can do lots of different things. It's very general. And we're starting to see, and I'll talk about some of this shortly, we're starting to see quite a bit of work in this field of general AI assistance. And then the fifth definition or element of this that I think is important to capture, I've already hinted at this a little bit, but it's actually going out into the physical world. So science doesn't just take place on your laptop or your desktop, right? Scientists work by doing experiments in labs or experiments in the field. And if we really want to use AI to accelerate, automate, augment scientific discovery, we have to look at that part of it as well, the lab part, the field part. And that's where robots have to come in. So we're going to need to develop robots that can actually automate scientific tasks, either in a wet lab or out in the field doing field work. So those are the 5 definitions. I'm going to focus on the last 2 in this talk. The general AI assistance and some very, very early work that we're doing looking at trying to get robots to automate tasks in labs. I don't know why that's happening. Let's go. Yeah, before I do that, though, I just want to tell you a story about why we got interested in this problem. And the reason that we got interested in this problem is because if you look across the whole of CSIRO, our best guess, there's probably about 1,000 scientists across CSIRO in different domains that are now applying AI in some way, shape, or form. And the problem that we identified was that they were all doing their own thing. They were all having to learn AI tools, figure out which AI tools to use, which would apply to their specific problems, and then applying it to those very specific problems. So not in this kind of general AI assistant way. So what we've been trying to do for the last 2 years is to move from that mode of AI being applied to very, very specific problems to having a general AI assistant that could be applied to multiple different problems across different domains. And just to give you an idea of the kind of domains we're talking about, I want to give you 4 examples of where AI is being applied by different scientists across CSIRO. I'm also always keen, by the way, to highlight the people behind scientific advances, because we often hear about scientific advances and we get very excited about the technology, and we forget that there are really, really smart people who came up with that stuff, and we should be celebrating those people. So let's celebrate some of these people. This is David Ireland. He is probably one of the world's foremost experts in AI chatbots for health. He has developed, way before ChatGPT, AI chatbots in a whole variety of applications to, for example, help people with speech issue due to Parkinson's, due to autism spectrum disorder, chatbots that would help people to stop smoking and things like that. Interestingly enough, if you actually talk to David and ask him, what was his motivation for coming up with these AI chatbots for these applications in the first place, he tells the story of his own 3-year-old son. And his 3-year-old son was autistic, and so by the time he got to be 3 years old, was really struggling with speech. And one day, David noticed that his son was actually using Siri to talk to, and that Siri was actually quite a good way for him learning how to pronounce words and how to talk in a conversational way. And that led David to what has now become a kind of lifelong piece of research, developing AI chatbots to help people with all kinds of conditions. So some great work there. This is Ivy Wong. She's from our Space and Astronomy research unit. She discovers galaxies using AI. How cool is that, I always thought AI was the coolest thing in the world. Space is pretty cool as well. I used to work for NASA, so that's cool. But to do AI in space is probably the coolest thing you can possibly do. Ivy does that. So what she does, she's trying to discover galaxies that have not yet been found out in deep space. And essentially the way it works is that there are plasma emissions that galaxies emit. And so if you look at a kind of picture of a certain part of the sky, you'll see kind of plasma all over the place. And the task is to figure out which bit of plasma belongs to which galaxy, which starts to sound a bit like an AI problem, right? Because you can train that on known galaxies and how the plasma kind of organizes itself. And it's almost like a computer vision problem to start drawing bounding boxes around pieces of plasma to say, well, that's actually a galaxy over there. So AI for discovering galaxies. This is another cool one. This is something called HairNet, which is an AI system that has been developed to figure out how hairy a cotton leaf is. So cotton leaves have little hairs on them. And it turns out to be really important to understand the length and the width of particular bits of hair on a particular cotton leaf, because the hairiness of the leaves determines how resistant to disease, what kind of yield you will get with that cotton plant. It's a very, very manual process right now where kind of agriculturalists kind of have to kind of walk up and down a field and touch leaves and make notes. These people in CSIRO developed an AI system that could automatically take images of these cotton leaves and figure out how hairy they were, and therefore make predictions about disease, resistance, and yield, and so forth. And then my final example is Dana Bradford, who is looking at AI to analyze the brain. So our brains, as we age, shrink. And if you get conditions such as dementia, it will shrink even more. And so she's trying to use AI to predict how much the brain will shrink, or how much the brain is shrinking in particular people, how much there is cortical thinning going on, which could potentially be used to kind of predict early onset of dementia and things like that. So that's just 4 of over 1,000 examples of how AI is being used across CSIRO. If you're interested in hearing more about those, you can go and have a listen to my podcast. It's called Everyday AI, and some of these kinds of stories are told in that podcast. But the reason for me introducing them today is because back to this idea of moving from AI being used to solve very, very specific problems to trying to come up with a general AI assistant, this is a good example of how that problem manifests itself in real life. We've got these 4 people of 1,000, each applying AI to a very, very specific problem. Could we come up with a general AI assistant that they could all use, even though they don't have to learn how to use AI, but then they could do their scientific work much quicker? Another way to look at this problem is this graph, which shows that if you look at scientists across a range of scientific domains, you're going to see a kind of normal distribution. At one end, you're going to see scientists who will be kind of early adopters of AI. They'll be technically savvy. They don't have any issue kind of going and learning about AI tools that are available and applying them in their work. At the other end of the spectrum, you're going to have people who are just kind of, so used to doing things in a particular way that they never want to touch AI. But it's the people in the middle that we're trying to target. People that don't necessarily have the technical knowledge of AI, don't know how to go out and figure out how to use these AI tools themselves. But if we were to give them a general purpose platform, they could pick it up and in a very easy way, using their own domain knowledge, their own domain vocabularies, they could actually apply AI to their own problems. And there's a study out there that says that in the case of biological science, those people on the left, those AI-savvy scientists, are probably about 18 to 20% of all scientists. It's the other 80% that we need to target and need to give them these kind of general purpose tools. And that's what we've been trying to do, essentially trying to democratize AI access for scientists. So I'm going to talk a little bit about what we've been doing in this space for the last kind of 12 to 18 months. So we've started a project called Science Digital. We are building an agentic AI platform that is meant to be used by any scientist across any scientific domain to do their kind of scientific work and help them to automate kind of scientific workflows. Not full automation. The whole purpose behind this is that it's a collaborative tool to be used with scientists. We already have a first version of this, although I will say it's still fairly early days, so this is emerging. I'll show you a video of it in a second. But just to give you an idea of what it is, there are a range of different agents in this platform. And they range from kind of, off-the-shelf kind of large language models that you can use for doing literature surveys or deep search tools that you can use. All that stuff's in there. But there's also more kind of specialist agents. So we've been focusing on genomics as a first use case, for example. There are tools that have been developed over the years in CSIRO, such as gene editing tools, that we've packaged up as agents and made them available in this environment. And so what this enables you to do as a scientist is you can either define your own workflows, where you've got these agents kind of working together in different ways to do things like suggest scientific hypotheses, to run experiments and so forth, to do literature surveys and all of that. Or there's a kind of meta agent that can try and do that orchestration for you. But I think I might show you a video of it actually operating in practice.
Let's use AI to supercharge science. Introducing CSIRO's latest digital innovation, an agentic AI-first operating system that's transforming how scientists work by seamlessly connecting physical, digital, and social systems, accelerating discoveries that once seemed decades away or entirely out of reach. Built by scientists, engineers, and AI product designers, this system helps you create and execute intelligent workflows that respond to science domain agnostic and to science domain specific requirements. Tell the system what you would like it to assist you with, and the AI agents will handle the legwork. From hypothesis generation to experimental design, from the virtual lab to the physical lab, brainstorm, verify, and refine new research ideas. Design, run, and simulate experiments and analyze data to gain new insights and build knowledge. Working with AI agents will empower scientists to make discoveries at an extraordinary pace without having to compromise the scientific method. The system can even spark entirely new research ideas, opening doors to discoveries that might never have even been explored. Our MVP is built for and by researchers in the health and life sciences, supporting digital and wet lab work. This is just the beginning. The system is already assisting scientists across disciplines as CSIRO researchers test, expand, and harness its capabilities to accelerate scientific discovery. Designed as a fully integrated platform, the system is purpose-built to support scientists, embedding key scientific best practices like data privacy, transparency, reproducibility, explainability, reasoning, and human oversight. It's responsible by design, with ethical and safety principles embedded at every stage, from data handling to decision-making, and a strict adherence to the scientific method. CSIRO is your trusted partner in innovation. We welcome opportunities to showcase and grow the platform's impact. Reach out if you'd like to learn more or explore a partnership. Please email scicedigitalprogram@csiro.au.
That gives you a sense of our agentic AI platform. It's not public yet. We've been working on particular use cases so far, largely in the health and life sciences domain, genomics in particular. We've had some early successes. You know, the genomics researchers that we've been working with have already said that there are tasks that they might have given a PhD student to do and that would have taken months, suddenly just take hours. So there's some early evidence that you can get quite rapid kind of scientific productivity increases from something like this. And we're going through a phase, actually it was launched this morning, where we're going to get a kind of first cohort of scientists as kind of early testers to really stress test this thing. I do want to just talk about some of the design principles that were kind of a little bit kind of mentioned in the video, but just to emphasize them, because these are important when we come to doing science. We've got a big responsible AI team within Data 61, and we've done a lot of, I would say, groundbreaking work on best practices and guidelines, including advising the Australian government on how to do AI responsibly. And we're building all of that into this platform. It's really, really important to do that when you're talking about science, because trust is everything in science. If you don't have trust in scientists, you've got nothing. And so you can't have a platform that is kind of, doing unethical things, right? So we are, as much as is possible, we're building in responsible AI guardrails as a primary artifact of design, not as an afterthought. Same thing with privacy as well. There's also a high level of transparency in the agents that are in the agent ecosystem. Of course, hallucinations is going to be a problem here, right? You don't want to be making up data and then making scientific claims based on that data. So how do you prevent that? I wouldn't say we can prevent hallucinations entirely, but what we can do is, as much as possible, we can make sure that these agents are actually transparent about what they're doing, and they're explaining what they're doing. So that's a kind of key design principle. It's important to point out that it's cloud provider agnostic. So you can use any LLM you like, it's just an agent. You can use any kind of cloud provider you like, it's just an agent. And that, again, is kind of built in as part of the thing. And as we'll see shortly, what I've shown you just now in that video is just the kind of virtual part of this. But as I've already said, if we really want AI to do end-to-end science, it's going to have to operate in the physical world as well. And so we've started doing some early experiments of getting robots to automate scientific tasks. And I'm going to talk about one of those experiments that we've done so far. So CSIRO, one of the things that CSIRO does, it has something called the National Collections. And this is a facility where there are millions of specimens of flora and fauna that have been collected over the years. In fact, 15 million specimens of all types of different insects, fish, plants, just about everything you can imagine. And they sit in a facility. They are an incredibly rich data source for scientists, particularly scientists who are working on biodiversity. By studying these specimens over time, you can understand changing biodiversity patterns. There are new specimens that are coming in all the time because there are discoveries of new species that are happening over time. But right now, all of those specimens are collected in physical form. They're not digitized. And that makes the science behind these specimens very, 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 very slow. And so the National Collections Facility is currently going through a process to try and digitize those collections. Now, this turns out to be a very, very repetitive, boring process. And I've watched it in action, so I can tell you exactly what it looks like. If you take the example of plants, for example, they're typically kind of plants that have been pressed onto a card, and that card has all kinds of information. So when they are digitizing this information, imagine the following scenario, because it's a real scenario. And that is that you've got a big box of cards, you've got a photo set up, so you can take photographs of those cards, and as a scientist, you spend your day picking up a card, putting it underneath the camera, taking a photo, making a few tweaks on the computer screen where that photo has come up. You put the card back in the box, you pick up the next card, you put it under the camera, you make a few tweaks, you put the card back in, you pull another card out, and you do the same thing all day long, right? It's very repetitive. It takes a really, really long time. So it's those, and that's not the only example of scientific labs that have repetitive, boring tasks. What if we could automate those repetitive, boring tasks using robots? And that would free up scientists' time to do something a bit more interesting. And that is what we've essentially been trying to do. I don't claim that we've nailed it yet, but it gives you an idea of where we're going. We've been doing it with the insect collection. This on my right here is a picture of what the insect specimens look like. They're typically on like a very, very, very tiny pin, and then there's a tiny kind of little card that has got some scientist from 2 decades ago who scribbled on what it was. And so we've created a robot that, given a tray of these specimens, can pick up the specimens, can read the information on the little card, and can digitize that for you. Obviously quite difficult to do, not least because, there's computer vision involved, the writing is very, very small and so forth, but just picking the thing up, you don't want to damage the thing in the process, right? So you've got to have very, very sensitive robotic arms. So creating a robot to do this in a traditional way where you're designing a robot just to do that one specific task would be hard enough. But we thought it's not hard enough. We'll try and make it harder. Because what we want to do, we want to effectively create general-purpose robots that could do multiple tasks, i.e. we want to look at kind of, training up foundation models that can do lots of these different tasks, so they're not specific to one particular task. So in this case, the training that was done for this model was it was trained on a whole bunch of data that was a combination of simulations, but also humans controlling the arms and therefore kind of training by imitation. Turns out you need about 50 of those imitations from the humans, combine that with simulated data, and you can start to get something that can automate this process. And if you do that, this is what it starts to look like. So no insects were damaged in the making of that video, I have to point out. So it's obviously early days, but that's, I think, where we see a vision of the future, is it's not just kind of, ChatGPT-like systems that are helping you do literature surveys or come up with hypotheses, but it's robotic AI assistants that will actually help you do real scientific experiments in the real world. Now, we're not the only people to be looking at this. Okay, there are a few others out there who are trying to build these kind of general AI scientific assistants. I like to think about plotting them on a graph that shows which part of the scientific method they are trying to assess. And you can really think of the scientific method as in 3 parts. The first part is just understanding what problem it is you're trying to solve, generating hypotheses, understanding the scientific literature. The second part is once you've got your hypothesis, is carrying out the experiment to actually do it. But the third part, science doesn't stop there. Science doesn't stop once you've done the experiment, right? Science only stops once you've got real solutions in the hands of real people, either through commercialization or impact on policy or some other kind of product approach, right? So there's the third part, which is the impact and commercialization. Now, some of you may have heard of the tool Sakana AI Scientist. Sakana is a Japanese AI company. They brought out, quite famously actually, something called the AI Scientist, which is trying to fully automate end-to-end the scientific process, all the way from having an original idea, a hypothesis, to running an experiment, to actually writing the scientific paper, writing the academic paper. They've got a lot of attention, not least because they recently ran an experiment with a workshop in one of the major AI conferences where they used AI to fully generate a paper that was submitted to a workshop, was peer-reviewed by humans, and was accepted into the workshop. I don't think that's the first time that's happened, but it's one of the early times that has happened. It's a very interesting piece of work, quite different from what we try to do, I think, because we're very much about having the human in the loop, because I don't think not having the human in the loop is the way to go. Right now, they're quite limited to a specific type of problem, a specific type of machine learning research, but they've been able to achieve quite a lot in that kind of end-to-end, go all the way from an idea, run a simulation, an experiment, essentially, and then generate a paper for that. There are other examples out there. Stop working. Yep, there we go. So there's some work at MIT that was actually presented in a workshop earlier this week called SciAgents. This is in the domain of materials design. And they also take an agentic approach. And they're using knowledge graphs. That's probably the thing that distinguishes them from some of the other attempts to do this, is that for that particular domain of materials design, they have a knowledge graph, and then they basically have kind of agent LLMs that kind of traverse over that knowledge graph and try to do things like generate hypotheses and generate simulations and so forth. You might have heard of Google's version of this, because again, got quite a lot of attention, the Google AI Co-Scientist. Again, it's an agent framework, so they have different agents, one to generate hypotheses, one to kind of evaluate the novelty of those hypotheses and so forth. They're really, right now, only focusing on the hypothesis generation and validation part. They're not actually running the experiments using the AI. We do work with Google. This is Google DeepMind project. We're actually working with them very closely. And we share information about the different kind of things that we do. And then there was a paper that came out of Stanford on something called the Virtual AI Lab, which again was an agent approach, and they had different agents designed to mimic scientists from different domains working together. So you might have an oncologist AI agent and a genomics AI agent, and you get them to kind of work together, and they solve problems for themselves. So there's, I would say, kind of growing interest in this field, lots more work to be done. And as you can see from the way I've plotted them on this picture, most of these general AI scientists are working towards the left side in the kind of hypothesis generation. What we're trying to do, and again, I'm not saying we've nailed it yet, but what we're trying to do is go all the way from the left, the far left, over to the far right, which is where you need to get into actually using robots to actually run experiments in real labs or in the real field, plus actually using AI to help you understand the market out there for products and so forth. So let's just talk about quickly to finish off, some broader considerations of all of this. Is it a good thing to be using AI to try and do science? Because I always think with AI, just because we can do something doesn't mean we should be doing something, right? So we should always be asking that question. And there are definitely some kind of caveats to be aware of with all of this. I've already said that trust in science is paramount. It's important that the public trust science. If we start generating a whole bunch of scientific papers that are full of hallucinations and then putting them out there in the world, we could very quickly lose that trust, right? So we don't want that. So hallucinations are, and I don't have answers to any of these, but these are the problems. Hallucinations is definitely one problem. Replicability, that's a core tenet of science, is you can take somebody else's work, you can replicate it to test that it actually works in practice. Is that going to be possible if we've got AI systems that are black boxes and can't really explain what they do? Scientific misconduct. There are an increasing number of papers being retracted from academic conferences for various reasons, but one of those reasons is that there are an increasing number of papers that are in some way being written by AI and may have errors in them that were generated by AI. There's also an increasing number of papers that are a peer review that is being done by AI. In fact, there was a study by Stanford University that showed that in one particular area, 17% of peer reviews of academic papers are now being done by AI. I won't ask you to put your hands up, but think about how many of you are doing your peer reviews by AI. Is that a good thing or not? Don't know. But we could, if we're not careful, increase the amount of scientific misconduct once we start using AI. And we also don't have good benchmarks about how can we test the results of AI for science. All these benchmarks on kind of maths Olympiad for general purpose AI, we don't have an equivalent thing for AI for science yet. Other issues that we have, what we're really trying to do here is democratize the use of AI in science, but that doesn't come for free. You can develop the best tool in the world, but just because it's the best tool in the world doesn't mean people will use it or know how to use it. You need to back that up with training for scientists and show them how to use it, even if it's a really good usable tool. There's also a risk that we create another digital divide in AI for science, because it might be that the rich countries have access to these kind of tools, the compute power that might be needed, whereas the poorer countries don't, and so they're no longer able to do that kind of science. And AI safety. I know that the Google AI co-scientists, for example, put a lot of thought into this, because if you're not careful, you've got an AI system that can come up with hypotheses by itself. It might come up with the hypotheses for a new chemical weapon, or teach people how to do things that we don't want them to be doing. So how do you prevent that? And then finally, what if we do get into this world where AI is doing a lot of the science for us? What does the future of science even look like? Does the nature of the tasks that we do as scientists fundamentally change? And probably it will. If you've got AI generating papers, you're going to change from spending most of your time writing the paper to checking the paper and making sure that the results that it's produced are actually valid. Is it actually going to make scientists more productive? There are early studies coming out now about Gen AI in general that show that productivity increases can be mixed. We don't really know. And also, is it going to make us more creative or less creative? So there's a whole bunch of things that we need to be aware of. I am going to finish at that point, so we've got a little bit of time for questions, but I just wanted to show you one final video, which again is some of the work that we've been doing on Australia's Great Barrier Reef. And this video, I think, illustrates the reason why we do what we do in CSIRO and why we think applying AI to some of these big scientific challenges is worthwhile doing.
I had seen coral reefs before, but only on black and white TV. When I was 5 or 6, saved up enough to get my first mask and snorkel and a set of fins. Seeing it in color in such abundance was a revelation. The Great Barrier Reef is great because it's the longest continuous stretch of reef on the planet. There are a number of issues affecting it. The one I'm involved with is the control of crown of thorns starfish. It's not like one of those cute little cuddly starfish. They're covered with poison spines, and they eat large amounts of coral very quickly. There are more of them now than there ever used to be because of things that people have done. The way people survey to find starfish outbreaks is to use the manta tow technique. You can only tow divers at a certain speed, and then they have to stop every 2 minutes. Someone records what they've seen, and then you continue until you've gone around the whole reef. So it can take all day or longer.
We teamed up with CSIRO, Australia's national science agency, to see how we could combine our expertise to solve this problem. CSIRO created this data set with starfish labeled and developed an EdgeML platform that runs TensorFlow models. The goal was to map out the starfish in real time. Using insights from a competition we ran with the Kaggle community, we were able to train a machine learning model to identify crown of thorns starfish and then create a map with all of the GPS locations of all of the different starfish we detected.
Through this machine learning project, we're going to enable teams of divers to quickly suppress the outbreaks.
We just had a human go out, and we also collected GoPro footage, and the human saw 1 crown of thorns starfish, and the object detection model picked up 20.
When we started working on manta tow over 40 years ago, people were still using punch cards, right?
Exactly.
So, no, we couldn't envisage this at all.
This project has the potential to scale broadly beyond the Great Barrier Reef.
Well, we all care about different things, I suppose, and have different value systems, but I grew up as a child in Papua New Guinea snorkeling. And you've just seen it degrade over 45 or 50 years. It is important.
This project really makes me feel hopeful for the future of the Barrier Reef.
And that's why we do what we do. Thank you all for listening. I think we've got a few minutes for questions, but thank you very much. There's one here. I don't know if there's a mic or yeah.
So my question would be, what's your expected acceptance by your staff, from senior to youngsters, on using or integrating like this Google, AI assistant, research assistant into, well, everyday work, right? So this is...
Yeah. So I'll just yeah, it's a good question. I'll just repeat the question. So the question was, what is our expected acceptance by scientists? You know, it's a really good question. Look, we're probably in the exploratory phase. So we've had a group of kind of early testers, but I would say they are very much the kind of early adopters. They're people that are following this kind of AI technology very closely anyway. So they're kind of the easy bit in a way. We just launched it today with a much broader group that will include people that have zero knowledge of AI. So I think the test will be, to what extent do they want to embrace this and use this. But our aspiration certainly is that, you know, most scientists within CSIRO would be using this tool. And then if that goes well, that we would actually make it available outside CSIRO and to other research institutions in Australia and across the world. But yeah, great question, thank you.
So you are positive?
I have to be positive, right?
Any other questions?
Thanks, John. That was an awesome talk. You had on one of the slides how Science Digital was wanting to span right from, you know, hypothesis development to impact and commercialization. I was just wondering if you could expand on how AI can help the commercialization side of things.
Yeah, that's a bit we haven't really done a lot of work on yet, but you know, you can imagine some obvious things. So there is an agent in the system that's kind of patent search, for example. So you can, you know, you can easily put agents in there or imagine agents that will do market analysis or do patent searches that will help you to understand if the problem you're trying to solve has a potential market at all. And certainly I know from my colleagues at CSIRO, including people like yourself, who do that kind of market analysis work, it can be very time-consuming and so forth. So I do think there's an opportunity for AI to help to automate some of that. But then by putting it in this platform, you integrate it with the other bits of the science that are going on rather than a completely standalone thing.
Okay, hello. Thank you for the great talk. So this year we had a couple of Nobel Prizes for AI. Do you think in the near future we will have some Nobel Prize to AI?
Oh, to actually the AI itself?
Yes.
Oh, that's a good question. I guess there isn't really a Nobel Prize for computer scientists other than the Turing Award, so I don't know. But I don't know. I mean, yeah, I don't know how to answer that. Let's hope so, you know?
Another question. Thank you for the excellent talk. You talked about the importance of people's trust in science, and I'd imagine that like the scientists' trust in this tool is also very important. What do you think, like, how do you, I don't know, help scientists like actually have trust in this tool that you're building? What's important there?
Yeah, that's an excellent question. Look, I think there's two parts to it. So one part of it comes back to that slide I had with design principles. So being very open and transparent about the fact that we've got responsible AI kind of built in from the beginning. And the fact that I think our team has got a very strong reputation globally for doing kind of responsible AI work, that engenders trust. I think probably the other part of it is that, you know, trust as a concept, even between humans, is not a binary thing, right? It evolves over time, and you have to grow that trust over time. As well as you and I get to know each other, I would learn to trust you more, and then based on your actions, I will either trust you more or trust you less, and I might trust you more one day and trust you less the other day. It's probably going to be like that with AI tools as well. And you see this even with like ChatGPT, right? You know, different people have different levels of trust. As they see things coming out of the tool that are right or that they can quickly validate, they grow trust in that. But we probably, as scientists, need to remain skeptics at all times, because I think there is a danger that you could trust these tools, but they're still making mistakes, and you're not checking it anymore because you kind of trusted them, and then you fall into a trap.
Thanks for the talk, John. So my question is about scientists of the future. If AI is increasingly used in science, how do you see future scientists, PhD students, postdocs really learning via some of the repetitive tasks or the time-consuming tasks? So how do you see scientist training changing with increasing adoption of AI in science?
Yeah, look, another excellent question, and probably one that I don't have an excellent answer to. Look, probably the easiest answer I can give to that is that it's probably going to be the case that all scientists, no matter what discipline they come from, will need to be trained in some way in AI. We saw that with some of the data I presented that says that, you know, even back in 2022, 6% of all academic papers are using AI. That's only going to increase, right? So much as in other fields, if you want to stay relevant, you're going to need to be on top of AI in some way. How do you do that? There's at least one university that I know of that is now making AI courses mandatory for all students across the university. I think it's University of Adelaide. Probably other ones across the world. That I think is an interesting approach, because at some level it becomes like maths for scientists, right? It's just a tool that is there and you have to use, and if you're not using it, then you're going to be losing to the competition. Yeah.
Okay, our last question.
Thank you for the great talk. So my question is about the robots that you were talking about, like your last example and another example you gave when the robots were sent down underground into a mine. So how do you feel the robots in the future will be used? Will they mostly be for tasks where you want to go into places that are hard to access, like underwater or space or anywhere? Do you think they can also replace humans where, like in the kitchen, will they have enough dexterity?
You know, I made a pledge to myself a while back that I would not try and predict the future when it comes to AI, because every AI prediction is wrong. So there's actually only one AI prediction I make nowadays, which is that if there's an AI prediction, then it's wrong. Look, at some point, I think we will have kind of humanoid robots in the home doing those kind of tasks. My suspicion is we're quite a long way away from that. Robots are pretty dumb, actually. And it's easy to kind of get swept away with some of the fancy demos that we see circulating online. But I'm always reminded, somebody showed me a video from, I think, 20 years ago of a media release from a university where they got a robot to fold laundry. And it looked amazing, and everybody thought that, you know, in a few years we're going to have laundry folding robots in our homes. I still don't have one. Maybe you have one. I don't know. But I still fold my laundry myself, or don't fold it, as the case may be. It's very hard to predict when these things will come, because even some of the kind of applications in more constrained environments that we're trying to do, we've got other work going on in factories, for example, of kind of cobots, and it's hard, you know. But yeah, who knows?
Thank you. I totally agree with you with the lack of ability to predict the future.
Yeah.
So on these words, many thanks for coming here, John, and thank you for the super presentation.
Thanks for listening, everybody.